Hi friends again. So today is the third of the series of lectures on radiation heat transfer, and in today's lecture we will be dealing in more detail with gray diffuse surfaces and energy exchange between gray diffuse surfaces. In the last class we went in detail about understanding radiation intensity and said that radiation intensity is a directional and a spectral quantity, and on the basis of the definition of radiation intensity we tried to derive the expressions for the emissive power, which is again an integral of the radiation intensity over spectrum and the wavelength, over the spectrum and the directions. And in directions also we said that in spherical coordinates, looking at direction over a hemisphere, it's an integral over two angles. One is the zenith angle, which is the angle with respect to the normal, and the azimuth angle, which is the angle on the plane. So any quantity which represents energy emission in radiation is a quantity which needs to be integrated over the directions and the spectrum before integrating it over the space and time. Right? Energy itself, normally, let's say emission from any given surface or the energy being given out from any surface or taken into any surface, is usually represented in terms of heat flux, which is the energy emitted or energy coming out or going in per unit area. So that is the spatial integration required. If there is a variation over space, you will need to integrate it over the space. And similarly, it's per unit time. And so if you want to find out the energy which is absorbed or emitted over a period of time, then we integrate it over time as well. So even both in conduction as well as convection, we had the spatial and the time variation. In addition to it, in radiation, the extra complexity is that you will need to integrate it over the spectrum and the direction. So we said that in our first course, we will try to spare ourselves with these details and say that we'll oversimplify the case at the risk of being simplistic, that we'll only consider in this particular case the problems in which we have only gray surfaces, that is the surfaces whose radiation does not depend on the spectrum. They have the same radiation properties over the spectrum, and diffuse surfaces, that is the direction independent emissions. We all said that the black body is a direction independent emitter, so it's a diffuse emitter, and it is the maximum emitter per unit surface, which basically means that its emissivity is always 1 in all directions and at all wavelengths. In gray diffuse surfaces, we will basically be dealing with non-black surfaces, that is the emissivity will be lower than 1, but we will still deal with surfaces whose emissivity is uniform in all directions and in the spectrum. Okay, so suppose I say the emissivity of a surface is 0.3, I normally indicate the hemispherical total emissivity of this surface is 0.3, which basically means that in all wavelengths of the spectrum, it emits 30% of the radiation that a black body would have emitted, but it emits uniformly this amount of radiation in all directions. Right? This is basically what we mean. So now let us use this gray diffuse assumption and start looking at radiative exchange between surfaces. Okay. So all of this time we looked at a single surface from which radiation is emitted or into which the radiation will get absorbed. Now we are going to deal with pairs of surfaces, that is two surfaces facing each other. How do they exchange radiation, particularly when the radiation can be termed as gray and diffuse. Okay. So let's begin with that now and try to understand how we can calculate gray diffuse radiative exchange between surfaces. So we'll be dealing with gray diffuse surfaces. Okay. So suppose I have a certain surface here, okay, whose area is dA1, and it emits to, let's say, a surface area dA2, which is at a distance s from the area dA1. So the amount of energy that is leaving dA1 and arriving on dA2 will depend on the emission over this solid angle omega, or d omega 2 is the solid angle that this area A2 subtends over that direction. Okay. So if this is the normal n1 vector to surface 1, and if this is the normal n2 to the surface 2, okay, and the angle this one makes, let us say, is theta 1, the angle this one makes is, let us say, theta 2. Okay. Now let us find out what is the amount of energy that leaves surface area A1 and arrives surface area A2. So we would like to know what is dq dot dA1 to dA2. Okay. So that will be given by the intensity of radiation emitted by surface A1 multiplied by this direction. Okay. Now we are looking at gray diffuse emission only. So let us say this intensity is uniform over the entire hemisphere. So the energy arriving on this will only be this solid angle, okay, corresponding to this solid angle that is coming on this side. So this is going to be equal to I1, which is already integrated over the hemisphere. You remember I lambda E prime, okay, multiplied by dA1. This is the energy emitted over the area dA1, and you would also have cos theta, sin theta, d theta, d phi, okay, and d lambda. This is basically what we used to have. So dA1 cos theta, d omega, d lambda. This is the integral that you will need to get for dq dot. Okay. This is basically what you needed to get. But now, since this is uniform over the entire spectrum, the energy that is required will be uniform over this whole area. So you can just, instead of integrating, you can just multiply. So this is actually d omega 2, okay, and the integral over lambda can be taken away, and so this lambda will go away. So basically you will get, so this is dq lambda initially. So now if I integrate over lambda, I will just get dq dot going from dA1 to dA2 will be I1 into dA1 cos theta into d omega. That will be the only angle, only thing that we need to consider. Okay, this integral over d lambda 1 has already been done. Okay, so you get, this is the energy in all wavelengths that is emitted from surface 1 that arrives on surface 2, which will be I1. I have removed the direction superscript by a prime from here, and I have removed the lambda from here. So it is becoming a gray diffuse intensity. So I1 multiplied by dA1 into cos theta, that is the projected in that direction, dA1 cos theta into d omega, which will be the I'll call it as d omega 2, which is the solid angle that is subtended by the surface 2 on surface in that direction of emission from surface 1. Okay. Now let's try to expand this. So what is d omega 2? D omega 2 will be this area dA2 projected normal to the radiation. So it will actually be dA2 cos theta 2 Okay, so for this area is projected normal to the thing, so the area that will actually be seen will be dA2 cos theta 2. That comes from the directional thing that we showed in the previous class in this slide. So let's try to understand that. Yeah, so if this is the area dA1, then projected in the direction which is at an angle theta to the normal is dA1 cos theta is the area that you see. So similar, if this is dA2, then the area projected normal to the line or ray that is arriving from 1 would be dA2 cos theta, right? That is exactly what I was just talking about. So let's come back to this diagram then. Okay, so this is dA1 or dAi in this particular case. Okay, and this is Ni, which is the normal to that, and the line of radiation that reaches dAj, which is actually dA2 in our case, is at an angle R. We said S in our diagram. Let's just look at that. And the normal to this is Nj, and this is angle theta 1. So dAj cos theta j is the one that is normal to this direction, and therefore dAj cos theta j divided by R squared will be your d omega ji. Okay, so that is basically what I was trying to show you. So let's come back to the diagram that we were looking at. Okay, so it is dA2 cos theta 2 divided by S square, which will be this d omega 2. So d omega 2 is dA2 cos theta 2 divided by S square. Okay, so if I substitute that into this expression, then what do I get? I get dq dot dA1 to dA2 will be equal to I1 dA1 cos theta 1 into dA2 cos theta 2 divided by S square. Okay, now I'll need to get an expression for this is elemental area 1 to elemental area 2. If I integrate this over the areas A1 and A2, I'll basically get the energy that is arriving on surface 2 from surface 1. Okay, so the total energy that is leaving surface A1 we can calculate by integrating this over area A1. So this will be dq dot dA1. So this is the energy leaving A1 but arriving on A2. The total energy leaving dA1 over the entire hemisphere will basically be the integral of this dA2 cos theta 2, basically d omega 2 over the entire hemisphere. Okay, so if I can do that integration, then I'll have an I1 dA1 and integral of cos theta 1 into sin theta 1 d theta d phi over phi equal to 0 to 2 pi and theta equal to 0 to pi by 2. Okay, so this is the integral. So I1 dA1 d omega, okay, and integral over the d omega over the hemisphere. Now this integral we said will be equal to pi. So this is pi I1 dA1. Okay, so what is this quantity? The first quantity is the energy leaving surface 1, surface dA1 and arriving on surface dA2, and this is the energy that is leaving dA1 in all directions. So the fraction of the energy emitted by surface dA1 that arrives on surface dA2 will be the ratio of these two. If I take the ratio of these two, I'll find that the dA1, I1 get cancelled out, and there will be a pi in addition here. So if I write the fraction of the emission that leaves surface dA1 and reaches surface dA2, that is, out of this energy that is emitted by surface dA1, this much reaches dA2. So this divided by this will be the fraction of the energy that leaves A1 that arrives on dA2. Okay, so what will that be? That will be F dA1 dA2 will be equal to dQ dot dA1 to dA2 divided by dQ dot dA1. Okay, so this will be the fraction of the energy that is leaving dA1, which actually arrives on dA2. The rest of the energy goes out in the rest of the hemisphere, right? So if I construct a hemisphere over this area dA1, then some amount of energy that leaves here reaches here, the rest of the energy goes out in this. So the second term is the one that leaves here and goes out through the entire hemisphere. The first term is the energy that leaves here and goes over this. So this divided by the total is what you get as the fraction. Okay, so this fraction is dQ dot dA1 dA2 divided by dQ dot dA1. And if I substitute for these two, if you can compare these and this, you can see that the I1 will get cancelled out, the dA1 will get cancelled out, okay, and the pi will get appended to the bottom. So I'll get F of dA1 to dA2 will be equal to the I1 dA1 will go, so it will be dA2 cos theta 1 cos theta 2 divided by pi s square. Okay, so this is your fraction from elemental area 1 to elemental area 2. Now we can integrate this to obtain the fraction of the energy that goes from surface A1 to surface A2, dA1. So there is a surface A1 here, out of which we have taken a small element dA1. So this is A1, this is dA1. Similarly, there is a surface A2 here, and we have taken an element surface dA2. Okay, so this is the normal N1 and this is the normal N2, and these are connected like this here with the distance S. So now we have written between elemental area dA1 and elemental area dA2. Now that needs to be integrated over the surface A1 and surface A2 to say what is the amount of energy that leaves this surface A1 that reaches this surface A2. This is an important result that we will need every time we want to calculate the integral. So if I do that integral, basically I'll need to integrate these quantities over area A1 and area A2. Okay, so let us write the expressions dQ dot for A1 and dQ dot for A1 to A2. Okay, so just like we wrote for dQ dot for dA1 to dA2 and dQ dot for dA1, we'll need to write dQ dot for A1, which will basically be nothing but this expression integrated over the area A1. Okay, so it will be A1 I1 pi if I1 is uniform over the area A. Okay, in the same way, this needs to be integrated over area A1 as well as A2. Okay, so there is a dA1 here, there is a dA2 here. It needs to be integrated over both of those areas in order to get the energy emitted from A1 to A2. And then the ratio of the two will give me F A1 A2. Okay, so let me try to do that. So dQ dot A1 is nothing but integral over area A1 of pi I1 dA1 if I can take I to be uniform for a simple case, this will actually become pi I1 A1. Okay, so this is the total energy. I can remove this D here because it's not an elemental area anymore. So it's Q dot from A1, the energy emitted by A1 over the entire hemisphere around it. Okay, that is the energy emitted by Q1. And Q dot A1 to A2 is nothing but double integral of dq dot dA1 to dA2 over areas A1 and A2. Is that correct? So in this one, if I take, this is equal to double integral, which is over the area A1 and A2, I1 into dA1 dA2 cos theta 1 cos theta 2 divided by square. Is it correct? So now if I take this I1 to be uniform over surface A, then this integral of A1 can be performed first, so this becomes A1, and since we are looking at gray diffuse emissions over the area A2, also it could be okay, so this I1 can be taken out of both these integrals. It will just come out just like that there, so it will actually become I1 into double integral of A1 and A2 this. So if I take the ratio f A1 to A2, which is nothing but this divided by this, that will give me, the I1 would get cancelled out, the pi will go underneath and 1 by A1 will come. So that will be a 1 by A1 integral over A1 and A2 of dA1 dA2 cos theta 1 cos theta 2 divided by pi square. Okay, so now this is the fraction of the energy emitted by area A1, gray diffuse surface area A1, that actually arrives on surface area A2. Okay, so this is actually this divided by this quantity. So what is interesting about the expression on the right hand side is that it contains no information about the intensity. The intensity values drop out because it is uniform over the area A1. So it is entirely dependent on the geometry. Okay, so this fraction, that is the fraction of the energy emitted by surface A1 that actually arrives on surface A2, is purely a geometric quantity and can be evaluated once I know what the geometries are. Okay, so this therefore is called the view factor or the geometric configuration factor. Okay, so and we can also simplify the notation of writing this by simply writing, if you can drop the a's, you can just say F12. Okay, so F12 basically represents the fraction of the energy that leaves surface 1 and reaches surface 2. So the order of the surface numbers is important. F12 is nothing but 1 over A1 into this. Now if I bring the A1 to this side, I get a symmetric expression. So I get A1 F12 is an integral, double integral over A1 and A2 of dA1 dA2 cos theta 1 cos theta 2 divided by pi s square. Now if I just take this expression and swap 1 and 2, because area 1 and area 2 are arbitrary, if I just swap 1 and 2, I get A2 F21, which is basically area 2 multiplied by the fraction of the energy emitted by surface 2 that actually arrives on surface 1. If I just swap the indices 1 and 2 here, nothing changes here, so it remains the same as A1 F12, which is equal to the same double integral area A1 A2 dA1 dA2 into cos theta 1 cos theta 2 divided by pi s square. Okay, so this is what we call as a reciprocity relationship. Okay, so if I know the fraction of energy leaving surface 1 and reaches surface 2, that is F12 is known to me, I can simply calculate F21 by multiplying it by A2 by A1 or vice versa. Okay, so you don't need to do this integration separately for each surface, but if I know for one surface, by reciprocity it is possible to get the view factor for another surface. Okay, so why is this important? This is important because in radiative heat exchange, suppose I have, let us say, two-dimensional enclosure, triangular enclosure, let us say surface 1, 2 and 3. Okay, then the radiative energy exchange between these interfaces will need to be calculated by knowing how much is the energy that is leaving this surface and actually arrives on this surface, how much is the energy that is leaving this surface and actually arriving on this surface. And if I get the total energy leaving this surface, then I should be able to evaluate the energy arriving on each of those surfaces. Okay, so this energy exchange calculation will require the view factor expression that we have just derived. We'll do the energy exchange calculation as we go on a little further. But now let us understand the properties of view factors. One is that it's a purely geometric quantity, and second is that it is the reciprocity relationship is valid. Okay, now let us look at a plane surface, let us say A1. So the energy that is leaving this surface can go to any other surface but cannot come back to itself because the energy travels in straight lines, the electromagnetic radiation. So long as the surface is planar or convex, the energy leaving a surface will not directly be seen by itself. But if I have a concave surface, then part of the energy leaving a surface can intercept the same surface again. Okay, so if I look at Fii for any surface I, this will be equal to 0 if it is convex or planar, and not equal to 0 if it is concave. What do we mean by convex, concave and planar? Convex is a surface which is protruding like this. So the surface of let us say our scalps or heads, the heads is a convex surface. Okay, so the energy emitted by our head will never return to our head directly. It has to be reflected or re-emitted by another surface for it to be able to return. So if my head is, let us say, surface I, then Fii for my head is 0. Similarly, for a plane wall or a plane floor, the value of Fii would be 0. But at the same time, if I take the surface, for example, of a kadhai, a vessel that we make use for frying in the kitchen, it has a concave surface. So from the inner surface of the kadhai, when energy is emitted, it will always intercept, part of the energy will intercept the same surface. Okay, the same kadhai put upside down, when it emits, it will not return to itself because no straight line that is leaving this surface will be able to intercept the same surface. So one thing is the self view factor of a surface of itself is non-zero only for concave surfaces, and for convex and planar surfaces it is 0. So this is one thing that we'll need to know. The second property, of course, is reciprocity. So A1 F12 is equal to A2 F21 for any pair of surfaces 1 and 2, because when we derived this expression, we did not make any assumptions other than gray diffuse. So long as the surface is black or gray diffuse, a black surface is also a gray diffuse surface with emissivity equal to 1. So a black or a gray diffuse surface, this can be directly used. Okay. And the third relationship for reciprocity is that if I have a closed enclosure, suppose I have drawn a 6-face enclosure. This is a 2-dimensional enclosure. Let us say it is infinitely long in the 3rd dimension. Okay, so the cross section is 2-dimensional. So if I call these surfaces 1, 2, 3, 4, 5, 6, the energy leaving surface 1 and reaching all the other surfaces of the enclosure. So if I add Fij for j is equal to 1 to 6. Okay, so this will be equal to 1, which basically means that the energy that is leaving this and going in any direction will intercept any one of these surfaces and will not escape these surfaces. So if it's a closed enclosure, then the summation of Fij over the closed enclosure is 1. In this case, I have shown all planar surfaces, so Fii will remain 0, so it will only be 2 to 6. But in the general case where any one of these surfaces, for example, is concave, this expression is valid. So this is a more general expression. The summation over all surfaces of an enclosure of radiation view factor will be 1. So this is simple logic. The fraction of the energy leaving a surface and reaching the other surfaces will be 1 if all the energy leaving the surface reaches one or the other surfaces. Okay, that's for the closed enclosure. So that is the third rule. The fourth rule will be that if there is a symmetry, then we can use the view factors to be the same. Say for example, if I have a surface like this and I have a perpendicular semicircle on both sides. So this is surface 1, which is emitting to surface 2, and the inside of the surface is surface 3. Then by symmetry we can say F12 will be equal to F13. Okay, this can apply to many other examples also. Suppose let us take cuboid. Okay, now if I am looking at the enclosure inside the cuboid, okay, so let us say this is surface 1, 2, 3, 4, 5, 6. Then 1 to 2 and 1 to 4 are symmetric. Similarly, 1 to 3, 1 to 5 and 1 to 6 are symmetric, and so on. So you would be able to eliminate the need for calculating view factors of many of the cases, and we should be able to use the summation rule and the symmetry rule to find out many of these view factors. Okay, so symmetry is when the geometrically symmetric cases occur. So the floor of this has the same view factor with this vertical, similarly this vertical and this vertical. Okay, so 1 to 2 and 4, and similarly 1 to 3 and 5 will be identical. So that is the case of symmetry. Okay, so this is another thing. And if I use reciprocity on this, A1 F12 is equal to A2 F21, and similarly A1 F13 equal to A3 F31. if A2 and A3 are equal, I should also be able to say F21 and F31 will be equal. So that's another thing that you'll get. Okay, so F12 is equal to A2 by A1 into F21, and F12 is also equal to A3 by A1 into F31, because F12 is equal to F13. Then we can also say F21 equal to F31 if A1 and A2 are equal in this particular case. Okay, so that is another way. So you can actually use these geometric manipulations to be able to get the various view factors. The fifth regulation, or the fifth simplification that we use, is what we call as superposition. Okay, so suppose I take a look at okay, two surfaces. Let us say this is surface 1, and let us say this surface is split. So this is 2 and this is 3. Okay, so then if I say the surface 2 plus 3, so F1 2 plus 3, okay, 2 plus 3 is this whole rectangle, okay, will be equal to F12 plus F13. This is plain logic. The fraction of energy that is leaving 1 and reaching 2, and the fraction of energy that is leaving 1 and reaching 3, when added together will give me the fraction of energy that is leaving 1 and reaching surface 2 plus 3. This is the principle of superposition. This is again useful in simplifying various cases. Okay, so that's the principle of superposition. Okay. Now using this, we should again use reciprocity and find out what happens to F23 to 1. Okay, so A1 F2 to 1 to 2 plus 3 will be equal to A2 plus 3 into F2 plus 3 to 1, and we can get relationships between A1, A2, A3, F12, F2, F12, F23, F2 plus A1 to 2 plus 3, etc. So that is the simplification that we can get from that. Okay, so say for example, A1 F1 to 2 plus 3 is equal to A of 2 plus 3 into F2 plus 3 to 1. Now this is nothing but A2 plus A3 into F2 plus 3 to 1. Okay, and now if I substitute for this expression from this, then I'll get A1 F1 to 2 plus 3 is equal to A1 F12 plus A1 F13, that is equal to A2 plus A3 into F2 plus 3 to 1. So you can get F2 plus 3 to 1 from this expression itself, which is A1 F12, A1 into F12 plus F13 divided by A2 plus A3. Okay, so that's a way we can use reciprocity and superposition together to get this expression. Okay, F2 plus 3 to 1 will be equal to A1 into F12 plus F13 divided by A1 plus A2. Okay. The last but not least is a very ingenuity based relationship called the hotel cross string rule. which is another way of finding out the radiative view factors in the case of two-dimensional geometries. For three-dimensional geometries, it's not directly applicable. So, but suppose I have a two-dimensional geometry with arbitrary sections. So, let us say I have a long furnace whose walls have this kind of a shape, let us say. Okay, and so let us say this is surface 1, this is surface 1, this is surface 2, this is surface 3, and this is surface 4. Okay, so if I want to find out the relationship between let's say 1 and 2, suppose this may not be there. Suppose I have a wall 1, which is the floor of the furnace, and wall 2, which is an arch at the top, and I would like to find A12. What is normally advised is you take a stretched string, a string which is non-elastic, and tie it at one end, just tie taut between these two. So let us say one parallel string here and another parallel string here between the two ends of 2 and the two ends of 1, and you also get if this is a concave surface, then you also put a string on top of this like this, then you put two crossed strings like this. Okay, so let us say this string, this is a straight one, so this has a length L1, and let us say this has a length L2, the straight one here, and let us say this is L3, this is L4, and the two diagonals, let us say, have L5 and L6. Okay, so the cross-string rule tells you a method to find out the view factor between surface 1 and surface 2, irrespective of whether they are convex, concave, or planar, by using stretched strings like this. So it basically tells you F12 is nothing but L5 plus L6, which is the sum of the two crossed strings minus the sum of the two parallel strings L3 plus L4 divided by twice L1. This is the rule that it tells you. These surfaces can be anything. Say for example, surface 1 itself is like this, and surface 2 itself is like this. So for surface 1, I would tie a taut string from this end to this. So here it will go along with the surface, and here it will be this. So the length of 1 is this one now. And similarly here between these two, I put a taut string. So this is L2, irrespective of what the length of the real surface is. Okay. So then if you use the cross strings between these, then the same formula would apply like that. Okay. So this is the ingenuity of this method, the cross-string method. So it gives you methods for calculating F12, even if the surfaces are slightly irregular. So this is the sum of the diagonals, the sum of the lengths of the diagonals, and this is the sum of the lengths of the parallel surfaces that you have constructed, diagonal surfaces, and this is the length of the string, that the surface whose view factor you are trying to find with the other, okay, multiplied by 2. So this is the Hotel cross-string method. So these are various methods using which you can actually evaluate radiation view factors between different surfaces, different pairs of surfaces. Okay, we can take examples in our tutorial class and try to find radiation view factors using these methods, so that you get a little bit more familiar with the radiation view factors. Okay. So today we'll just stop with radiation view factors, try to read through the material that is given to you and understand what the implication of the radiation view factors is. In next lecture, we will actually use the concept of these view factors for the heat exchange between radiative heat exchange between gray diffuse surfaces in enclosures. So we'll develop the expression for radiative balance for an enclosure and work out a couple of simple applications of the radiative energy balance for gray diffuse enclosures. we'll stop here in this class. So in case you have any questions about this, you could either email to me or send me a query on Moodle, and I can respond to you. Okay, I'll open a question answer forum, a discussion forum on Moodle today, on which you can post questions in which you have doubts, so that others can also see your question and my response can also be visible to others. Okay, today I will open a Moodle forum on your Moodle page, so that the discussions and questions answers about all the lectures that we have done so far would be posted there. So you can post your questions. I can ask the TAs also to be active there. So let the TAs try to answer some questions. I will answer some questions, so that your question answers session that normally used to happen in or outside the class can be substituted. Okay? So we'll stop here and continue in the next lecture.